Whereas in particle physics, it tends to be, oh, everyone's thinking about dark matter. That's the thing I should be working on, dark matter. And it's like, yeah, that's a strategy for research that I find can be problematic when the motivation is just to be part of the crowd. Mm-hmm. But it's more just the number of people, right? It's like, is this subject making so much progress that it warrants the attention to it, or are we ignoring subjects that are making real progress and need more people? And is that healthy for the field?
Any sufficiently advanced technology is indistinguishable from magic.
Welcome, everybody, to the first episode live in studio of the Into the Impossible podcast. In many, many years, we are emerging from pandemic podcasting. And no one could be happier than I, your fearful host, formerly fearful host, Dr. Brian Keating. And I'm joined today with a renowned cosmologist, a collaborator, a colleague, Professor Dan Green. Welcome, Daniel, to the Into the Impossible podcast.
Hi, Ryan. Great to see you.
Good to see you, too. So we're recording live. This is an experiment. Studio is still a little bit ghetto. It's going to improve. Got big guests coming up. Today we're talking about Nobel dreams, or maybe not Nobel dreams. No, Gary Taubes is not here. This is kind gift for Eric Weinstein from Martin Bauer. Kind of strange turn of events. We'll get into some other time. We're talking about things that aren't necessarily Nobel recipients, but are potentially Nobel worthy. And it's really prompted by Daniel's amazing tweet storm of the month of December, which caused him to really gain a tremendous amount of well-deserved attention for his perspicacity and everything that he does. He's an amazing colleague, and I'm so glad that we poached him away. And I want to give him an introduction, but I want him to do it so I don't get anything wrong. And that will commence right now. So, Dan, where do you come from? What's your origin story? We're cosmologists. You're a theorist. I'm an experimentalist. We've worked together on many projects, including the Simons Observatory. And what's your origin story? Tell the audience, where did you come from?
So I grew up in Vancouver, British Columbia, Canada. I was a science fair and enthusiast and amateur astronomer as a kid, and stayed in Vancouver to go to the University of British Columbia for undergrad. And there I, interacted with a bunch of the local famous people like Bill Unruh, who's famous for the Unruh radiation. And after spending 4 years there, I was ready to make the big move to the United States for graduate school. And I went to Stanford, where I studied with Eva Silverstein, who's well known in part because she's a MacArthur Award winner. But she is one of these interesting people who bridges the boundary between many fields. She's a string theorist by training, but's really interested in cosmology. And while I was there, many other things like condensed matter physics. And so she was kind of a very broad person who liked to investigate different interesting things. And so that rubbed off on me in a certain way. And so after graduate school, I moved to Princeton at the Institute for Advanced Study, and I tried a bunch of different fields out. And in part because of the presence of David Spergel and Matthias Saldiaga, who are just some of the most brilliant people I've ever met, that kind of their unique style of just kind of doing everything in cosmology was really intoxicating, and I kind of became a cosmologist from that point forward. And so from there, I went back to Stanford, and then eventually to the University of Toronto at the Canadian Institute for Theoretical Astrophysics,
where we poached you from.
Yes, indeed. And so I was there. I also got to meet Dick Bond, who's another just incredible cosmologist with great stories about the history of the subject that I had never been exposed to. So a lot of, even in my list, a lot of the sort of when I was thinking of, what were big things, I would think back to conversations with Dick where he would kind of been like, oh, at this time, it was really, this thing is really what moves the field. And so was a very useful perspective for me. And then I moved here in 2017, and I've been here ever since.
You've been here ever since, and you're now associate professor, which means you're tenured, which means you could speculate on all sorts of crazy stuff like I like to do. Maybe have your own podcast someday. And certainly you're a must follow on Twitter. And I think I recommend everybody do that because Daniel is, I think you're unique in a lot of ways. You have a very high command of experimental results in the history of the experimental field. And I always say, and tell me what you teach your students, but I always say that experimentalists, my students should understand theory as well as your graduate students do, but they're not required to create new theories. Do you feel, well, first of all, how do you react to that? Do you think theorists should have to understand experiments but not do experiments?
I think, I mean, it's different people have different styles. So for me, there's always like, I don't think there's one right way to do it. But, what drew me to the subject of cosmology is the ability to go. So I can distinctly remember a meeting in Princeton where in the span of one meeting, David Spergel had kind of brought up why a telescope they were designing was going to have swinging mirrors. And then at the same time was talking about topological defects in the early universe from a theoretical point of view. And for me, that the idea that a single conversation could cover all of that ground and that one person could be in command of all of those things at the same time, that was amazing. Yeah. And I think it's not for every subject, right? If you're in particle physics, like there's a very hard line between really doing experiment and doing theory, because if you join the experiment, there's like rules. You can't publish certain things if you're part of the experiment. And so I actually just, that seems problematic to me. It would be nice if everyone could find the balance between how much theory, how much experiment work for them. But to your point on coming from the experimental side, I do remember there's like experimentalists. Sometimes they hate it when theorists say, "Oh, we need theorists to calculate things." And they're like, "I can calculate just fine." Don't tell me I don't know how to do math. It's more it's the new ideas, right. And that the health of the field requires an influx of new ideas, not just new calculations for testing experiments. So I think that a blend is great, and I think cosmology. That's the great thing about our field is that blend is very alive and well in a way that maybe other fields have become really split into theory and experiment.
Yeah, and I think that is something that has drawn me to remain in the field, dabble in theory, to whatever extent I'm capable of doing it. Always trying to have one of my students who is more theoretically inclined, so to speak. And thankfully, I've had a bunch that have been phenomenal students, and you've helped to kind of shepherd their careers through all the different hoops they have to jump through. And thankfully, they're back off their strike. We broke the picket line.
Just a quick pause to ask you for a small favor. While my thumb is occupied with old Albert on it, yours is presumably freed up to leave a thumbs up on this video. It really helps me a lot with a good old-fashioned YouTube algorithm. Thanks a lot. Now back to the video.
But I want to talk about this epic, tweet thread that you had, and I'll have my editor put that up on the screen as we're talking. It got millions of impressions and just tremendous feedback and a lot of attention. And I want to have you explain the predicate for it. What was the sort of impetus? Why did you choose to present it in this way? And how did you maintain your sanity and strength during the month of December? I can hardly post stuff that other people write for not. Nobody writes my tweets. But what was the impetus of it? How'd you come up with it? So,
it was one of these things. I think a lot about what's important research just for myself. And I tell my students to as well. I think it's valuable as an exercise as a researcher to know sort of what is something that would rise to the level of the best result of a year or the best result of 5 years, the best result of 10 years. And I tell them this in the same way that you would think about, like, what's your best movie of this year? Imagine you're a filmmaker, and you want to know what makes a good movie. We don't have to agree on what the best movie is of all time or even the best movie of the year, but we can probably agree that certain movies are good and certain movies are not so good. And obviously it's nice to aim to make movies that are good if you're a filmmaker. And for me, it's the same with research. I think everyone knows that Einstein's contributions to physics were important, but even if you aspire to be Einstein, no one just jumps into being Einstein. You have to have some more modest goals to tick along the way. And so I think that's what's often missing for me in the conversation around what's good and bad research is it's either there's Einstein or there's nothing else. And it's and I was just, I'm inspired all the time to be well, what's the middle? What was the best paper of the past 10 years? And then I don't know, just suddenly there's something. My kids have advent calendars. And so the month of December is a time where there's a kind of thing every day. And I just what, maybe it would be just fun to every day of this month, just put one of these kind of ideas out there for people to digest, and whether they like it or not, I felt like I could do that. It would be fun. And, it wasn't hard to get 25 interesting papers because I wasn't ordering them to be honest. If it was I was going to do the best paper, then the second best paper, I would have agonized way more. But it's just like, here's 31 papers I like. That's not so difficult.
All right. And so we'll go through a couple of the highlights, and some of them I just really could not agree with you more, and some of them I felt like, oh, why did you leave this one off? And so we'll talk about the one, the ones that were orphaned, the great results that you did. But there was one criterion, which was it could not have been appeared in this book or this book, Nobel Dreams or Into the Impossible, my book. And why was that? What was that choice?
It might it aligns with your missions pretty well, but actually the reason was just to make an interesting list. Like, I thought if it was like, it's like saying your favorite thing is puppies. Like, no one's going to disagree with that. Like, I thought to be an interesting list, it had to be a list of things that hadn't had the kind of like obvious acclaim that everyone can agree on. Because I'm like, yeah, this thing that won the Nobel Prize was a good result. It's like, yeah, great.
Right.
Like, no duh. But I thought, and again, I didn't just, Nobel Prize was the easiest line to drew, but I drew some other ones where I was like, that it's so obvious that everyone would have that on their list because it's so well popularized. And the fun of making a list is to give some light onto things that are sort of less well known. The same way that if you're a movie critic, like, that's why they tend to be less likely to put the blockbuster that made $1 billion on the list, because everyone knows that movie's out there. Yeah. And that's why they'll throw in that like weird foreign film that no one's heard of, because it's like, this is my opportunity to sort of cast some light on something I really appreciated. So that was the idea, not because I had any sort of thing against Nobel Prize winners or one way or the other, but just an easy
not
way
like
to exclude them.
I'm a vendetta. So where did you start off? What was the first tweet, and then the last tweet, and then we'll get to some of the ones that we can debate.
So I started with heavy quark effective theory. So heavy quark effective theory was this idea that when you're thinking about states of matter, or particularly particles that are made out of lots of quarks, or made out of quarks that include one whose mass is very large, there's a secret trick to understand what's going on, which is to kind of treat that one quark like it's infinitely heavy. And this trick has a way of explaining why a bunch of these sort of baryonic states tend to have similar properties, even though they're made out of different combinations of quarks. And this idea was like, this was the first example where someone had taken a theory that's written down, and by kind of expanding it in a non-obvious way, made new properties emerge that were not obvious from the beginning. So there's kind of secret symmetries that related different states of particles in a way that was, you couldn't have just said, oh, well, we knew that from the beginning, and you just made it obvious in some other way. And that's the kind of, that was sort of the first example, at least in my knowledge of the history of the subject, of sort of effective field theory, which is this great thing that has really transformed the field in the past 30 years, where effective field theory wasn't just a way of saying a result that people already knew, but really was a way of rethinking about what physics is about, where by focusing in on the scale of the problem you care about, what is the right way to think about the theory, you really make things obvious that were not obvious before. And so that has happened. There's been many, many further examples since. And I picked that one because I was like, this is the thing that kind of started it all. And our colleague Anish Manohar was one of the people who really pushed that forward in the early 90s, and has since discovered many other great examples of this kind of like mysterious things that come out of thinking about what the right way to organize physics problems is. And so that was one where it's like, I picked that one as the first one because it was the kind of thing where I feel like people who really know the subject know that heavy quark effective theory was important, but like, it's kind of niche. Like, not very many people know it, and it deserves much more credit as kind of spawning a lot of development of the field. And then the last one, which will be close to your heart, I imagine, was the age of the universe. This was sort of a measurement, and this was feeding back to our comment about Dick Bond. This was the one that drove me crazy because the history is that it was really first definitively pinned down by cosmic microwave background measurements. But Dick would tell me that it was the boomerang experiment and the analysis that they did around boomerang, which was before the satellite WMAP, which usually gets the credit for the measurement. That was a big deal. But the part of the reason I put it on my list is that when I was in Canada, I worked on a space telescope called MOST. Mm-hmm. And the proposal for MOST, which was made in the 90s, was that they were going to measure the age of the universe by doing astroseismology to measure the age of stars in our galaxies. And when the proposal was made in the mid to late 90s, the age of the universe was so uncertain that was a compelling thing to do. Like, we literally didn't know, is it 8 billion years or 20 billion years? And so pinning down how old stars was seemed like a really important problem. And while they were building that telescope, CMB came along and determined the age of the universe to basically 1%. And that suddenly became overnight not an interesting question for them.
It just obliterates everything.
Yeah. Right? Now, to their good luck, though, at the same time that they were, the fields were evolving, exoplanets came along, and a telescope that's really good at measuring very small changes in light of stars, really excellent for exoplanets. So while their age of the universe science target disappeared, exoplanets emerged. And so that was like, it's the give and take of science. But that one for me is very personally resonant because I was coming along right at that moment.
That was right when you were kind of hitting maturity and really coming into your own as a scientist and thinking about projects that could then take your interest.
So my first project on MOST was to do exoplanets. I was the first person who thought about exoplanets for MOST. And it was like, literally as an undergrad, they put me on this because it was like, this was not part of our proposal at all, but is obviously very important science. So it's the example of how new targets emerge in the middle of a project. Like, you don't just do what the project set out to do. And so serendipity exactly is a great
Now that project
story.
never...
So it launched. It launched in 2003, I think, on a Russian satellite, or Russian rocket. It was one of these converted ICBMs. I think at the time it was the rocket that had put the most satellites into independent orbits that had ever been done, using that great ICBM technology to hit multiple U.S. targets.
Swords into plowshares.
And so they had a couple of high profile papers around astroseismology, but they did, and they put some upper limits on exoplanets. But the thing that's really challenging with exoplanets is to see a light curve. You need to see the light reflected off the planet. It depends on the exact atmosphere. And so actually at the time, as an undergrad, I got to work with Sara Seager because she was the one who was making these.
Two-time past guest on the Into the Cosmos
podcast. And so she had these atmosphere models, and so we were using her atmosphere models to predict what it might look like. And they were so uncertain at the time, it was totally possible that most could detect it, and they ended up setting some interesting upper limits, but were unable to actually see what it looked like.
Fascinating. Okay, well, let's get back to the tweets in just a minute, but I did want to take a detour into a subject that's very, very prominently featured on this channel, which is the crisis in physics. So I've had probably 36 podcasts or interviews or webinars with my friends at PBS Spacetime and others saying, basically, is physics in crisis? We've had on guests like Sabine Hossenfelder, Neil Turok. The episode is called Physics is in Crisis. We've had on Eric Weinstein. We've had on many, many kind of iconoclastic people. But we've also had on many, supporters that physics is doing just fine, and we should stop the histrionics about what's wrong with physics. But let's talk about that. How do you react to these claims that physics is suffering not the crisis of tensions? Those are healthy. We'll talk about those, and we'll talk about some unhealthy, maybe corollaries to those tensions that people use tension or research direction or a lacuna in the Big Bang, CDM model to kind of cast doubt upon all of physics or something stupid like that. But we'll talk about it. I shouldn't say stupid. Strike that from the record. But clickbaity,
yes.
which I've been guilty of myself. But anyway, but let's talk about physics. Is physics in crisis? What is this notion that people seem to want to believe almost that we as physicists are chasing angels dancing in pinheads?
Well, I think what I would say is that as I try to emphasize, my thought process around what's good and bad science, I try to have a very, nuanced view because it's important for me as a researcher. And so I would say the thing that I will first say the thing I agree with, which in this context, it's typically around, are we crisis zeroing in on really one field? It's usually like, there's a group of people working on this one thing. Is this one thing going to lead for progress? And the reality is research is very complex. There's people doing all kinds of different things. And so to say physics is not making progress is often just completely ignoring huge swaths of the community that are making real progress. But the part where I would say that I at least agree with the spirit of it is that particle physics in particular has a phenomena where people tend to kind of, I describe them in physics terms, they're like bosons. They all like to do the same thing, right? They don't like, whereas fermions like to not be in the same state. So if one person's working on a subject, in other fields, like one person's working on a subject, like, oh, someone's got that covered, I should go do something else. Whereas in particle physics, it tends to be, oh, everyone's thinking about dark matter. That's the thing I should be working on, dark matter. And it's like, yeah, that's a strategy for research that I find can be problematic when the motivation is just to be part of the crowd, right? And if we don't have good checks on, are we making progress? And again, we could be making progress, but the question is the progress worth the number of people working on it? And so I think in a nuance,
typically hear about this string theory.
Yeah, so string theory is exactly the same, but I want to spread it, because string theory, the criticism is also that it doesn't make contact with experiment. And I would say I don't see it necessarily as being an issue of contact with experiment. There's great results that didn't intend to be in contact with experiment when they started that make contact later. And there's some of those on my list on purpose for that reason. But it's more just the number of people, right? It's like, is this subject making so much progress that it warrants the attention to it? Or are we ignoring subjects that are making real progress and need more people? And is that healthy for the field? And so I would say my point of view is, at times, I'm frustrated that there's not more people working on inflationary cosmology, a subject close to my heart, and that there's perhaps more emphasis on dark matter than maybe I find is warranted. But dark matter, I also think, is the correct theory of cosmology. All the data, and my point of view is absolutely correct, and we should definitely look for it. And there's just some, it's around the edges. How much attention does it warrant? Are setting bounds on models of dark matter that no one in their right mind thinks is the model of nature a worthy use of time, or should they be exploring more generally? And okay, those are, I think, legitimate things to worry about. Is the health of any field, as this, how does sociology affect what people feel they can and cannot spend their time on? Mm-hmm. So I think from that point of view, I agree that there's a reason to worry, but there's a reason to worry all the time. Right, like it's like the health.
People would say inflation gets way more attention than bouncing cosmological models. We've had an Aegis and Pulse.
So I would say in that example, I know the field in that case, and I would say, I think there's a lot in this sort of clickbaity way, which is like people, and I think this is true to most of the criticism, which I'll come to, which is the criticism also tends to paint researchers as not thinking about why they spend their time on what they do, and again, they think about it, but in this complicated way. They think about it both from like, if I choose to work on this thing, like, and not like, is it going to ruin my career? And not just being like looking at the job prospects and saying like, hey, there's not a job ad that says, to work on this weird topic, and that might influence what they do. But within any area that you're working on, you're not oblivious to why you pick one model over the other. So the reason people work on dark matter is not because they're not aware that it could have been explained by something that's not dark matter. It's because you can look at they've thought about the ways in which something is not dark matter might manifest, and the data doesn't support those kinds of ideas. And the same is true with bouncing cosmology. So from my point of view, I actually think the debate between bouncing cosmologies and inflation isn't the most exciting thing to me, because to me, they both solve the same problem in more or less the same way. Like, I don't see bouncing as really that big a deviation from inflation. It just slightly different. And I honestly don't care which one it is. I happen to think the data, it's easier to make a model of inflation. Mm-hmm. And then, so I work on inflation, but actually a lot of the tools I use would apply equally well to bouncing cosmologies. Yeah. So it's not, so I would say like the idea that I am absolutely, I'm religiously against bouncing cosmologists for some deep-seated prejudice. Like, I would be totally fine with a bouncing cosmology. If someone wrote a model that worked better than inflation, I'd be like, yeah, that's totally fine.
I kind of see it like, are you familiar with something called the Ikea effect?
No.
It's where they take people and they give them a piece of high quality furniture like this, which and they give them from Ikea, and they say build this table, and they build it, and then they have another group, or even the same group, and basically the same table, but they just give it to them. And the people that built the table themselves value it 10x what the people who just got it from a, so I feel like people are so invested in whatever paradigm. This is true, parallel law, independent of what field we're in. But it just so happens that you and I are both cosmologists, that we see it, that people are really entrenched in it. And so that's why people like Paul Steinhardt, who did have a lot of, so-called sunk cost, sunk cost fallacy into inflation, is so impressive to me that he can pivot, people that come up and just, their whole career have been entrenched in the Big Bang never happened and all these other things. So let's dwell a little bit more on string theory. A lot of the claims, and I had on Kamran Vafa, and I've had on Avi Loeb and Eric Weinstein and Sabine, and the claims that I always hear is that they don't make, testable predictions. They make a lot of retrodictions. And actually, to be fair, Kamran, he had a wonderful appearance in one of my most popular episodes. I'll put a link somewhere up there. And he said, no, Brian, you're wrong. String theory does make predictions. It predicts that the mass of the electron is, between 10 to the minus, 1 Planck masses to, 10 to the minus 30 Planck masses. It's in a range. It makes prediction. It could be, 10 to the 80th. That would be inconsistent. What do you make? And I asked him, I said, give me something that is a concrete, answer the skeptics. We have a saying in Judaism, know what to say to a heretic. So tell me, how do you react to that? I mean, is that what would you use?
Oh, so actually, I am not going to, my PhD advisor will be very upset if I were to not defend string theory very, very strongly. But to be honest, I don't see the value of string theory in terms of whether it makes experimental predictions or not. I think the attempt to put it into the does it predict particle physics or not, hasn't been very successful. And I know that there's, lots, I read all the papers when I was a grad student of people trying to make models of the standard model. And I don't find that to be particularly useful as a scientist who now does not spend most of my time doing string theory. However, I find many results in string theory useful to what I do. And a lot of what's called string theory is, now, the impact is sort of as laying the foundation for the laws of physics that we then use. So one of the examples I brought up in this, I brought up in this list was what's called the conformal bootstrap. And it's sort of, one of the applications is to try to make sense of, what are the restrictions on theories of quantum gravity that are inspired by, what we know about string theory. But the exact technique that is being used in that one case to understand quantum gravity and anti-de Sitter space, which is what lots of string theorists do, is actually also the best way we have to predict what will happen to helium-4 at this particular critical point that has been measured. And it's one of these things that's they didn't set out when they were thinking about quantum gravity to predict what helium does. That was not what anyone thought they were doing when they were thinking about black holes. But at the same time, it is making a real experimental prediction there. And it's really useful in that regard. And so for me, it's more the value of string theory as a research endeavor is more in that regard. As a person trained in string theory, as an undergrad, I worked on loop quantum gravity with Bill Unruh and, at UBC. And then I went to grad school and worked on string theory. And I use neither one in my, directly in my day-to-day work now. But the things I learned by learning string theory inform a lot of what I do. There's a lot of just ideas that came out of string theory that you can remove the string theory are super useful ideas. And they really change how I think about physics. The stuff I learned about loop quantum gravity has not been useful at all. Right. And so from my point of view, it's okay. And again, this is the attention thing, right? You could say, given how many people work on string theory, has it delivered enough? And I think that's a fair question to ask. But I wouldn't go so far as to say string theory is not useful, because there are many, many results in string theory that have really helped me understand the universe and come up with tests that we can do in cosmology to understand how structure was created in the universe.
Quick question. When you're looking at, and you and I serve on a lot of committees, we have, as I say, we have the hardest 3-hour-a-week job in the world. There's no way around it, Dan, right? I mean, we have these committees that meet, every quarter, but sometimes hiring committees, and we have to look forward to faculty, and we get 400 applications for a single position. It's so much more cutthroat than when you joined, let alone when I joined, the ranks of faculty 19 years ago. I can't believe it. But the point being, do you have a goal? Is there a rubric, string theorists wanted and loop quantum gravity? Obviously you're going to say no, we don't exclude anybody. It's based on merit. But talk about because people say, well, there's too much effort going into it. But I can't tell my student, I can't force my student. You have to work on the Simons Observatory or Simons Array, Polar Bear. I can't force it. If they don't want to work on it, they go to a different grade. They join your group or do something else. So to what extent do we really have any say to the people that say there's too much going into this field? How do you answer that? In a practical sense?
Well, I mean, again, this is where for me, it's part of taste. Right? If you ask someone what their favorite movies are and they're all terrible movies, probably not going to give them money to make their next movie, right? Because you kind of know what they're doing. And so if we hire someone who I feel has just a nose for interesting ideas and through that process, it leads them to loop quantum gravity or leads them to string theory. Like, I will trust that they have good taste and they know why they're doing it. Mm-hmm. But I don't also think that being dogmatic about it, like we will hire someone because we need someone who knows how to calculate some process in string theory. Like, we don't need people to calculate anything, as established before. It's the new ideas that we care about. So, I think what the great thing about our institution is that our theory group is very diverse in the topics they work on. But I think we all have both a common language of effective field theory. So I think that's usually the thing. If you don't understand effective field theory, it's hard to know what's an interesting problem and not an interesting problem. So what that subject has done for the world is it took the space of problems and it really organized them in a way where hard problems were obvious and easy problems were obvious and interesting problems were obvious. And so within our group, we all have a collective understanding of that. And so we can all communicate to each other. Some people were trained to string theory, some of them not, some of them very critical of string theory, some of them very supportive of string theory. But if you put us all in a room and you say, why are you working on this problem? They can instantly communicate to everyone else in the room why that's an interesting problem. And everyone will come away going, yeah, that's a really interesting problem. Yeah. And if you can hire people like that, like, that's fantastic. Yeah, like what they work on, like they'll tell you why it's interesting after they figure something out. And that's, I think, what's important.
Now talk about, let's get back to your tweet storm. So any controversial choices? Did you get feedback from your vast audience? So hopefully it'll grow, but anything controversial?
So I actually got less feedback than I was expecting. I was expecting to get a little bit more pushback on some of the choices. I would say the one obvious omission that I had, which was very intentional, was ADS-CFT, which is this idea that, quantum gravity and anti-de Sitter space, which is some space that's not our universe, is equal mathematically to conventional quantum field theory. And this was it's like the most cited paper I think it is like the most cited paper in theoretical physics at this point. And, I left it off. It was written in, 97. Mm-hmm. And I left it off for the same reason I left off Nobel Prizes. Not because also because, it evokes so many emotions when you bring up that paper because it's so well known. And for me, I thought, it's been incredibly useful for things that ended up being connected to experiment, but I'd rather zoom in on the things that ended up being that came after that ended up being really useful and clearly progress because everyone already knows about ADS.
Yeah. Mm-hmm. And then Supernova 1987A, that caught my eye. Talk about that. What did that mean?
So I put that, so I'm glad you caught that one because that was one I was proud of to have on the list. And again, to connect back to your many written documents about the Nobel Prize, like I like separating science from the people that do science. Like, the people that do science are important, but what I was trying to get at with the list is like, I don't care about who did it. I care about like the thing that was important. Right. And so putting an event and not a paper or not a thing was useful because Supernova 1987A, core collapse supernova in the Large Magellanic Cloud, it's the closest supernova we've been able to observe in the modern era where we have technology, particularly neutrino detectors. And so it was this unique event that a lot of people point to as like the moment when particle physics and astronomy kind of merged into this particle astrophysics because we had the direct observations with light, but we also had these neutrinos that came out of the supernova and showed up in our detectors. And like to this day, like there are many, many papers in particle physics every year that are like, this new person had this idea, but the observation of the supernova in 1987 rules it out. Because like it gives us this window into what happened at extremely high densities that we can't make on Earth. And like, it's just luck, right? Yeah. Like it's not like nobody wrote a proposal for that neutrino thing. I mean, they might have said, oh, if we're lucky enough that a supernova happens nearby, then we could do something with it. But the actual impact on the field has been enormous and long lasting because we don't get supernova like that all the time. Yeah. And so that was the one where I thought it was the most obvious, the scientific value of the event where there's no like person you point to when you say this was important because this person had this idea. It was like just important because it happened.
Right. Fun fact, that supernova indirectly led to me being here because it was discovered when I was in middle high school or late high school, early high school. And it was really, kind of surprising. I thought, oh, there's a supernova every century in every galaxy. No, we haven't had a supernova in a long time, and maybe that's a good thing. But it was discovered by, I think, Robert Sanduleek, who's an astronomer at Case Western Reserve University, which, as you know from my interview with Stacey McGaw and Glenn Starkman, that's where my alma mater. So talk about, so the next after kind of CMB, which I'm so happy makes such direct.
A lot of places on their list.
Honorable mentions, yeah. Although that could mean, we're due for more and more Nobel Prizes, right? Talk about the appearance of Susie. I mean, to some people they'd say, "Oh, Susie's ruled out," right? So, what extent is Susie ruled out, and why did it feature so? I did a histogram, in my head of your tweets, and Susie appears pretty frequently.
So I think the main tool use of supersymmetry in the instances on my list is as a tool to solve quantum field theories, and the reason I like to sort of put it in that perspective is that toy models are very valuable in physics, right? Like, and not even just in physics. Like, I think the Ising model, which is this model which we use to understand magnetism, is now like used to understand machine learning. Like, it's like they're like these toy models that we can solve and we can understand all the dynamics of are incredibly powerful in every domain of physics. So I'll give you a quote of this story. Steve Gibbelson, who's a very famous condensed matter theorist at Stanford. I took a class of condensed matter physics during when I was in grad school. And at the beginning of the class, before we'd really done anything, he said, if you want to be a successful condensed matter physicist, you just pick one of these models. Like, it doesn't even matter what the model is. Mm-hmm. And you study literally everything about it. You study what happens when it's a strong coupling, a weak coupling, at high temperature, low temperature. You just do literally everything. And then the rest of your career, whenever anyone comes up to you with a new idea, you say, oh, that's just like in the Ising model when it blah, 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 this happens. And it was a very useful comment, because that is the use of these toy models, is that they just give you a way to sort of, in a way that you can solve, understand what complicated systems do. And so a lot of the use of supersymmetry, whether or not it's true in the real world, is it allows us to solve for quantum field theories, like what happens in them that we literally can't solve in the ones that are closer to the real world. So we can understand nuclear physics in a supersymmetric world mathematically, improve all kinds of very important results that help us understand what real world nuclear physics could do, or real world strongly coupled systems where it's hard to solve the equations ourselves. And so as a tool, it's been incredibly powerful, just as a way to think about dynamics of, complicated systems.
Absolutely. So the next subject that I want to turn to, just in a couple of minutes we have before we have to get over to the faculty club for our Friday afternoon scotches, is our topics that didn't make the list. So sometimes that's even more revelatory than obviously you only had 31 days to make these epic tweet storms possible. But tell me a couple that if you had to go into, February, the shortest month. By the way, do you know which month has 28 days in it?
All of them?
All of them. Guys, smart. These guys. That's one of my dad jokes. What didn't make the list? What would you put on?
So do you want things that didn't make the list because of my rules, or things I would add to the list if I had more time?
Yeah, let's do one of each. One from each.
Okay, so I would say if I had more... one of them that probably qualifies that I didn't add to my list, not for any good reason, was the study of proton decay. Mm-hmm. So proton decay is we have all these really interesting theories that predict that protons should decay.
Right.
And we really don't have a good reason for thinking that protons are stable. And the study of proton decay was inspired by these grand unified theories that predicted it should be there. And it really took off in the 80s. And in the 80s, it really killed a lot of ideas that were at the time considered very realistic to be how the world worked.
SU5.
I think the sort of early like SU5 models that are not supersymmetric are dead. The supersymmetric ones are still alive. Mm-hmm. But if we could do better in proton decay, we could really just either find or rule out some of our most exciting ideas for grand unified theories. But it was this example of something that, it came out of theory, but it's a great test to do. And theory kind of motivated doing a thing we should have done anyway. And I think that would have made my list, because it was very influential of how people thought about particle physics. It kind of people thought they were really going to see it at the level predicted by these early grand unified models. And it was kind of the first thing that didn't go according to plan. Like, the standard model kind of came along and everything that it predicted was seen. Mm-hmm. And I think a lot of people in the 80s thought, okay, we saw the W boson. We're now going to see proton decay and everything's going to go according to plan. Right. And that was the first thing that kind of didn't go as we thought it might. Mm-hmm. And And I think in that regard, you might say like it was very influential, both in a good and bad way. But that was like, I mean, it's hard to overstate the kind of sense in which like both, if we ever saw anything, that would be incredible. Yeah. But just that the bounds that exist now are some of our most sensitive tests of physics that we can't see directly. So that was one. I think it would qualify under my rules, but I didn't want to dig into the history. Is very complicated of where do you draw the line.
Yeah, exactly.
And then one that didn't meet it because it failed my rules that I really love is this prediction that the absence of seeing temperature fluctuations in the CMB in the 1980s meant that there had to be dark matter. Yeah. So there's this great argument. So if you go back in time to when they first saw the CMB, they said, well, it's really smooth. Temperature in every direction is the same, but the universe we see is very not smooth. There's lots of stuff everywhere, planets, stars, galaxies. And this had to come out of that smooth starting point. And in a universe that only has the kind of matter that we experience, you can say, okay, well, there's big fluctuations today. There's planet Earth here, not over there. That's a big change in the density. And from what we know, given when we observe the CMB in the history of the universe and where we are today, the temperature fluctuation should be 1 part in 1,000. It can't be any smaller than that, or there's just no way it could have worked. And they didn't see it at 1 part in 1,000. They didn't even see it at 1 part in 10,000. So by 1980, they knew that there was no fluctuation at 1 part in 10,000. And people wrote this paper in 1982 that's like, that means there's dark matter. Right? Like, there's like, that's the only thing that that's the obvious thing I can think of that we have some kind of evidence for already. Right. But like, that's what's going on. Because otherwise we thought we were supposed to see it 1 part in 1,000. We're definitely not finding it. And that paper, so it fails my rule because I had said I was only going to take papers after 1983. Right. So, but then the second thing is it's technically cited in the Nobel Prize for Peoples. But people, I mean, it's kind of unfair because people got like it's like kind of like a career. Yeah, you can't say every paper that people ever wrote doesn't count for the list. But the other thing about it is like, if you look at the citation history, it was getting like 10 citations a year for, 40-ish years. I think that's criminal. It's such a beautiful idea that it really, like, I just feel bad that it didn't get more attention.
Well, speaking of Professor Jim Peebles, invited on the show. He had a great book came out last year. He also had 2 years ago now. And he had a wonderful paper called Anomalies in Cosmology, which came out late at the end of last year, in which he goes through all these tensions and kind of crises, but from a real, obviously the highest caliber of physicists walking Earth right now. I hope we can talk about that in a part 2 because and other things, the crises, the Hubble tension, dark matter crisis, other phenomena that we have, as well as how can we get more and better students around the world to come into physics, and what you're optimistic about in physics and what you're kind of hoping will change in our physics, both from the depth, the breadth, the diversity of who we can appeal to and bring in under the tent. But I want to thank you for spending this little hour with us in my audience. And you're going to be definitely an audience favorite. I hope you'll come back again soon and we'll talk many, many more times. And I hope I can call upon you whenever there's a calculation I don't understand. I'm actually not that good at it. I still have to sing the alphabet song to know what comes after R. It's embarrassing. Daniel Green, Professor Daniel Green, one of the brightest people I know, bluest flame thinker, in this neck of the universe. Thank you so much for joining us.
Thanks, Brian. This was awesome.